Yeah, good day everyone. I'll be looking at the topic called capacitors. These are devices that are used to store electric charges. They are passive components, meaning they do not require power to be activated. They only receive energy, which can be utilized in terms of energy storage and energy dissipation. Capacitors come in different sizes and shapes. Their uses are pretty impressive. We almost can't have an electrical or electronic circuit without a capacitor. Now that is the plain truth. Your Wi-Fi, your mobile phone, your television, your radio, your stabilizer, your UPS, your electric fan, your washing machine, your dishwasher, your microwave. These are many devices that do have a capacitor in them. So like I said, it's almost impossible to have an electrical or electronic circuit without the capacitor. Your adapter, meaning your chargers for your laptop, for your mobile phones, they do have capacitors in them. Now, capacitors can be used for quite a lot of things. And one of them is, we can use capacitors in car ignition system. We can use capacitors in tuning circuits like radio and television. We can use capacitors as a voltage doubler. We can use capacitors to suppress spark in an induction coil, as an AC coupler, as a bypass in amplifiers. We can use capacitors to block DC. We can use them as oscillators. We can use them in filter circuits. If you are an electronic person and you are involved in designing filters, maybe your low pass filter or your high pass filter or a band pass filter, you will see that most of these circuits do have a capacitor in them. A capacitor comprises of two metals called electrodes, separated by an insulator called the dielectric. The dielectric could be air, paper, glass, ceramic, etc. As long as it is an insulator, it can serve as a dielectric. It's actually these basic features that account for the symbol of a capacitor. If you look at the symbol closely, you will see that it's like two bars placed together, separated by a distance between them. So this first black mark represents the first electrode, while the second black mark represents the second electrode. The gap in between them represents the insulator. Now in this example, or in this symbol, it will look as if that it is air that is separating the two capacitors. So these are other symbols of capacitors. Capacitors actually will have two types basically. They can be fixed or variable. When we say a fixed capacitor is that capacitor that has a particular value, a fixed value, a specific value. So when you go to the market, for example, you can buy a capacitor that is 4 microfarad or 10 microfarad or 100 microfarad, depending on the value that you want. But a variable capacitor is that capacitor whose capacitance can be changed. So you might buy a 100 microfarad variable capacitor and you can tune it to change it to maybe 50 or 40 or 10 or 5. Well, in my other diagram, you see that capacitor symbol varies. We have different ways of representing a capacitor. Now in the UK, you can see the symbol on the screen, and for those in the US, they prefer to use what we have down there. Have you ever heard of a crystal capacitor? This is what a crystal capacitor looks like. And we use crystal capacitor in microcontrollers. I'll be showing that very, very soon. Now, a crystal capacitor works like this. When you send it a signal, it gets charged up, and more like a breathing capacitor. Now we use them in microcontrollers to oscillation for the circuit and to filter any noise that can come into your electrical circuit. This is a microcontroller, and if you are an electronic fan, this microcontroller is called the PIC 16F84, a very popular microcontroller. Now I have 3 capacitors here. The first one is a crystal capacitor. This is the crystal capacitor. Then this capacitor are start capacitor, the C2 and the C1. So in this circuit, they are helping the PIC 16F84 to remove noise, while the crystal provides oscillation. The capacitance of a capacitor. This is the ability of a capacitor to store electric charges, and it is the ratio of the charge of either plate of a capacitor to the voltage. So the formula for capacitance is C is equal to Q over V. Obviously, the SI unit is the coulomb per volt. Well, this unit is less preferred to the farad, which is technically the capacitance of a capacitor when a coulomb causes a potential difference of 1 volt. Now, when we plot the graph of voltage to charge, we'll get a straight graph, a linear graph. It is important that I show you that C is equal to Q all over V. The capacitance is our constant in this equation, so it means our variables are the charge and the voltage. So when we plot the graph of the voltage against the charge, what we get is a straight line, meaning as the voltage increases, the charge also increases, or as the charge increases, the voltage also increases. That is what graph like this depicts. The factors that determines the capacitance of a capacitor. Number 1 is the area of the metallic plates. Number 2, the distance between the plates. Number 3, the nature of the dielectric. Now if you check the formula below, you will see that the capacitance of a capacitor is E A divided by D, where E represents the permittivity of the dielectric, the C represents the capacitance in farads, and A represents the area of the plates in square meters, while D is the distance between the plates. Now from this formula, it is obvious that C, the capacitance, is inversely proportional to the distance, meaning as the capacitance increases, the distance reduces, or as the distance increases, the capacitance reduces. That E can be represented as E naught times ER, where E naught is the permittivity of free space and ER is the relative permittivity, which is 1 for air and vacuum. Now, if the insulator in a capacitor is air or a vacuum, then this formula can be rewritten to E naught times area divided by D. Now, we only use this relationship when the relative permittivity is 1. Or we can actually draw quite a lot of conclusions with a capacitor. Like I said, the capacitance of a capacitor is inversely proportional to the distance, and the capacitance of a capacitor is directly proportional to the area. Now, please do not forget that we have C is equal to Q all over V. So it will mean also that the capacitance of a capacitor is inversely proportional to the potential difference across the capacitor. So meaning as the capacitance, okay, these two are inversely proportional, but the Q and V are directly proportional. So please note that it's very, very important. Capacitors can be charged and discharged. To charge a capacitor, you will connect a voltage source, that is a battery, to the capacitor. And to discharge a capacitor, you remove the battery and connect it to an external load. So when you do that, the capacitor discharges. Now when a capacitor is charged, many times the charge on either electrode or the metallic plate will be the same. So we're going to have equal charge on both sides of the electrode. When the capacitor is discharged, there will be a leakage or transfer of voltage to the external load. I'd like you to quickly pay close attention to the graph of charge and time. As this capacitor here is charging, you observe that there is a rise in the charge with respect to time. So at the end of the day, we're going to have a circuit diagram that looks like this, more like a parabola moving in this direction. In my next video, I will be showing you capacitors in series, capacitors in parallel, and how to make calculations around them. I hope you enjoyed this video. Please like and subscribe, and please do not forget to comment. I'll be making videos and I'll be improving as you guys comment. Thank you very much. I will see you all in the next video. Work done on energy stored in a capacitor. Well, the energy stored in the capacitor is half QV. If we input Q is equal to CV, then we are going to get half times C times V squared. And if we replace V with the first formula, Q over C, then energy stored is half Q squared over C. It means that in physics, we have three formulas for representing the energy stored in the capacitor. The times QV and the second is half CV squared, and the third is half Q squared all over C. Thank you, ladies and gentlemen.